shall I get going then? Yeah, so hi, I'm Robert Virding. I think I'm probably the one furthest away. I live in Stockholm, so I don't know if anyone's further away than that, but yeah. And well, I work for Erlang Solutions now, but I will not try and do advertising. Like Oliver, I'm not going to try and do advertising here, although we are fantastic and we do a lot of very good stuff. So if you want some help, come to us. Yeah, that's my advertising stunt, my bit, right? So we're done there. So yeah, I was one of the original developers of Erlang back in the late 80s in Ericsson. I'll talk a very little bit about that, but not that much, so you don't have to worry. Oh, there's someone from India. You win. Okay, so someone's further away from me. All right, okay. That means he's got much worse hours than I do. Okay, so yeah, and so what I plan to go through is a little bit about Erlang history, mainly just to try and explain very briefly why it looks like it does, right? Because it's a bit different from most things, and there are reasons for it being a bit different. And then a little bit about the internals, about the beam. If you want to talk about that, I can tell me if you want more. If you want less, I can just cut it down if you haven't heard it. And then I'll start talking a bit about language implementations. Very, very briefly about Lxd and Lfe, because they're what I call native implementations. They're basically the same semantics as Erlang has, and a bit more about my luerl and my erlog, which are doing different semantics, and a bit about the problems that you have with that. And I have, well, a few small demos, and then we can see and have questions. And if you have questions or comments along the time, just take them immediately. You don't have to wait for them anyway. Just take them when you have them. And I think that's about it, right? So yeah. Any questions before I start? Any comments, any requests? Nope. Okay. Silent group here. Wow, there's a lot of people. Yeah, right. So we'll start. And I'll share the screen here, and I'll share my slides up here. And if I'm implying that I'm sharing, but I'm not, tell me, because that sometimes happens that I forget to do that. But we'll see what happens here. Right, so let's have a look, and we can view it, and we can enter the full screen. All right. So this is a little bit about implementing languages on the beam. Bits and pieces of this have been taken from other places as well too. So yeah, that's it. Can't do that. Yeah, okay. So this is getting back to a little bit why Erlang looks like it does, right? Because why it has the combination of things it does, and some things has some things, and some things it doesn't have. And these points are from a thesis written by Bjorn Decker, who was the boss of the lab in the 80s and the 90s, about some of the properties of telecom systems. So there are a large number of, I think you've seen these, but there are a large number of concurrent activities going on at the same time, a very large number. I mean, back in those days, even though you could have telephone exchanges with a few 100,000 lines coming in, you might be running tens of thousands of calls plus all the things which you're doing. So there's a lot of concurrency going in there. There are timing constraints, not just how long times think, but the system should never block. And when something happens, you expect to get a response very quickly within a certain time. Distribution. You have a very stringent fault tolerance requirements. And the only way to make a truly fault-tolerant system is run on at least 2 computers. That's nothing strange, right? And so there's basic support for doing that internally. The continuous operation and software maintenance, that means you just want to be able to upgrade the system while it's running and not stop it. And also have a very strict requirements about fault tolerance. So when things go wrong, you should be able to detect them, maintain them, control, and not take down the system. So the second worst thing that can happen is you crash the system. The worst thing that can happen is the computer crashes. Right? That's about it. Right? So there's a lot of these things, and this is nothing radical. Today, it's quite common in many various types of systems. But the thing was that so Erlang and the system around it, not just the language, but how we envisaged the language to be used, was designed to solve this type of problem. Right? That's what it's all about. And the Erlang OTP provides direct support for these things, for doing these things, because that's what it's all about. And a couple of things here. we were not out to implement a functional language. So I'd worked with functional languages we had before as well, but that was not our goal, right? To do that. And we weren't out to implement the actor model. I'd never actually heard of the actor model until afterwards. So I read a report or a paper, someone saying that Erlang implemented the actor model, so I had to go out and try and find out what the actor model does. And we did more or less, but we were trying to solve the problem. That was our goal, right? We had this problem. How can we solve the problem, this type of problem, in the best way, and provide support for doing that, the tools for doing that? This made the whole thing very focused, what we're trying to do. And we were very lucky in this sense as well, that we had a user group who were doing an architecture study, who weren't part of developing the language, but they wanted to use the language to look at their they were doing it for the architecture studies. And they could come back, they did come back very well with feedback on our ideas, on the language ideas and ideas of how you'd build a system and how you'd make things and stuff like this. They could very much well come back and say, yes, this worked. No, this didn't work. This was okay, but we couldn't use it, and things like this as well. So it was a very, very iterative process. We had ideas, we'd test it, they would test it, they would come back, and we'd go round and round and round and round like this. And this is what the language became. This is where we end up in something that the language worked, and the ideas of how you use the features in it to build systems worked as well. So where do we get? Yeah, first, I think you've seen this. Lightweight, massive concurrency. Millions of Erlang processes are on one machine, completely doable. They've been done. All the things around processes are very fast. Creation, context switching, process communication, everything cheap and fast. Right? It had to be this. Asynchronous communication, that's what we needed in our requirements. And also on top of that, you can build whatever you want. Right? I can show code if you haven't looked before about doing this. And you need it for non-blocking systems. Again, we're really worked up about not blocking the system. Process isolation, process dies, they shouldn't root other things. There'll need to be support in the system for detecting and handling errors, because errors are always going to occur. That's something we found, well, that's common, it is like this, but many times other systems that other people were developing just didn't have to attack the problem like we did. We also found that, well, okay, we wanted a high-level language. And now we're talking late 80s, okay? So things were quite low. We're comparing to things like Ada and C like this. We want a relatively high language. I think the second two are interesting in that. We wanted something where the language is simple, right? Simple is good, but it's difficult. Let's see, I have to find a quote here by Dijkstra. He's got a beautiful quote for this. Let's see. Wait a minute, let's get the right browser up. We'll find it here. Dijkstra, and we go that, let's see, quote simplicity. And he has one that says, simplicity is a great virtue, but requires hard work to achieve it and education to appreciate it, and to make matters worse, complexity sells better. And making something, getting the right level of simplicity, making the same small number of basic principles is difficult, because you have to work on it to find out the right set of things you need in there. And it's just so easy to toss in another feature. We toss in another feature, and we toss in another feature, a few more features to get what we want. And suddenly we've got a big complex mess in the bottom where things start interacting with each other and you lose control of what's going on. So the difficulty is getting the right set of features. And in this case, small is good. And it should be simple to understand, hopefully to program as well too. So we took a while to do it. This didn't come easily, but I mean, if you look at the concurrency model, there are 4 or 5 feature properties of it, depending how you want to count it. And same with the error handling, and that's it. With those, you can build anything you want on top of that. And also we found, provide tools for building systems, not solutions. Because at the time when we tried to provide solutions, we usually got it wrong. And we'd misunderstood the problem or how it was supposed to be solved and things like that. So we did a number of we added some quite fancy features to the language, but they were just wrong. Right? So yeah. So we end up, with Erlang, it's a simple functional language. It's a different syntax, but most functional languages are different syntax. And if you look at sequential language, it's pretty common. It's pretty standard functional stuff there. And there's lightweight massive concurrency. Yes, there's asynchronous communication. Yes, you have process isolation, error handling, and continuous support for continuous evolution of the system. which in this case means you can load in code while the system is running. It's very defined what happens when you load code. Other systems will allow you to do that while the system is running, but you don't really know exactly what's going to happen if I redefine a function, especially if I'm in the middle of using it. If I redefine the function, what's going to happen there? If it goes garbage and crashes the system or not. In Erlang, languages built on top of Erlang, this is very well defined. So that's the basics. That's where we're getting. So now we're going to go a bit bottom up here. And the thing is, of course, is what's the beam? Well, it's a virtual machine to run Erlang. Okay. By the way, beam originally stood for Bogdan's Erlang Abstract Machine. So do I have like this? Do I have something? No, I don't have this anywhere. So what happened was the language was originally developed in Prologue as an interpreter in Prologue. That was great for developing stuff, right? For working on things and making new things, for testing, because it made it very easy. But it wasn't very fast. And when our first user group decided they wanted to make a product, they said it has to go 70 times faster. And I did a big hack and I got it going 4 times faster. So we're way off. And that means we had to leave using a Prologue interpreter, and we wrote a virtual machine. The first one was called JAM, Joe's Abstract Machine, from Joe Armstrong. He wrote that. He designed that, and Mike Williams, he did, the third guy in the group, he did the C implementation. And that worked very well, it worked fine. But then we had another member of in the lab called Bogdan Hausman, and he did his own machine. And he started off by doing one which generated C code instead. And then you load in this compiler C code and load it in and things like this. And that worked very well. But it wasn't practically usable. I mean, it worked and no problems there, but it made the compilation was very slow and the code size was quite large. And then you try to run it so you could have some code compiled down to C and some interpret with a bytecode, and it just got the interface was not very good. So the C code disappeared after a while. But that's where the name Beam comes from. It's Bogdan's Erlang Abstract Machine. Now it's Bjorn's Erlang Abstract Machine has been overtaken. So I think that the only thing that's left from those days is the name of the machine itself. But it's a virtual machine to run Erlang. That's what it is. That's what the JAM was as well too. It's got all the things you need. All the properties of the Erlang language are built into the machine. So most of what you see running is done in the machine. So it's got the concurrency in there. It's got the asynchronous communication. It's the process isolation, the error handling, continuous evolution. All the support for all the things in the language are there. The soft real-timeness, this is there. The non-blocking, the fact you have a preemptive scheduler, that's not something that the Erlang code has to worry about or the compiler. That's all done in the machine. And the multi-core support, the load balancing, all this type of stuff is baked into the machine as well. And it's I don't know, how many people have played with or used Observer? Or some have, yeah. That is a fantastic tool, but that's the interesting thing about, I'll show you some examples later. The interesting thing about that is that is built on top of all the standard primitives you have for introspecting in the system. It doesn't have any backdoors or any secrets or anything like this. You could write your own if you wanted to. If you didn't like Observe and do something else with it, change it, just rewrite it, right? So you've got all these introspection tools that are in there built into the machine as well. And you've got to interface the outside world, the ports and the NIFs and things like this. So it's all in there. You've also got the language stuff. This immutable data you see if you're running Erlang or Elixir or Lfe for that matter, that is not something in the language that stops you from mutating data. It's not that you haven't got a function in the language to do it. That is built into the virtual machine all the way down. That's just something that's in the machine. You cannot get around that. You could do it with a NIF. NIF stands for natively implemented function. That's a way of writing code in C, which you can call from Erlang. And you probably could go in and start mutating data, internal data, doing that. Excuse me, but there's no guarantee what will happen if you just crash the machine or just gets really weird or things like that. So, but the immutability is always down there. And again, these were things we just thought were so important. So the pattern matching, there's support for pattern matching there as well too. I don't know if you tried running the compiler and do the uppercase S option to see what the assembler code generates, right? I can show you afterwards. Well, let's try it now. Let's see if we've got something here. I've got some code here. We're in the luerl. Let's see if we've got some Erlang code here. Trace test. Yeah, I can just do this. I'll just do all, and I'll do C here. I'll compile this, and I'll compile trace test. Hopefully there are no bugs in it, and we'll just use the uppercase S option here. Yeah, it is. It's something wrong there. See if I can find another one. Does anyone see another Erlang file there?
TTRL.
Where are we?
Third file.
Yeah.
Yeah, those are good too.
The GC after. Okay, we'll see if that works. Right, we'll see. Yes, these are a lot of test functions. That's the problem with them. So we'll say GC. If I spell it correctly, it's even better.
Needs an underscore.
Syntax errors. We'll try TT, see if that works.
I believe.
Yeah, that does it. Now, if we go out here, we can do Emacs of tt.erl, and this is the simple function for it. Now, if I go in here and do tt.s, this is the assembler code that the compiler generates. And if we go back here and look at, do I have any? Wait a minute, where are we? Am I doing any pattern matching down here? Yeah, we're doing some pattern matching inside the. Oh, we're doing some pattern matching inside the no try here. And if we go in and look here in the no try, here we see it's expanded the pattern matching to do things for it. So it tests if it's equal to integer 0, otherwise it does that, otherwise it jumps down here and does the test. So all the pattern matching has been expanded and the support for doing things like this. And here we see all the things that the compiler does at the moment for working with stuff. Right? It's adding line information, which will then be used when you get when you get errors running the code and things like this as well too. So yeah, there's a lot of support for all these things going on inside here. Yeah, and it's a functional. Yes, there is only a predefined set of data types. There are no user data types. There are no user-defined data types at all. You have a specific set of data types, and that's it, right? The way modules work is also put in the machine, and there's no global data. So we don't do shared, we don't do mutable, and we don't do global. That's just it. There's no support for doing that in the machine at all. Well, there has come some support, which is fantastic if you use it correctly. If you use it the wrong way, the cost is enormous. You can literally force the system to recompile all the modules running in the system. So you don't want to do that. But yeah, so this is what we're saying. There are no new data types. There are no user-defined data types. So if you're running Erlang, you've got records, they fake it. That just fakes it, puts it on top of a tuple. If you're running Lxd, you've got structs, they fake it, and they put that on top of a map. And yeah, so we don't even have, I don't know if you thought about this, but there's actually no string data type either. There's no character data type for that matter. We use integers for characters. Erlang uses lists of characters for strings, and Lxd uses binaries, UTF-8 encoded binaries for strings, but that's just a binary data type, so you can just break that if you want to. So there's only a very limited set of data types you have to work with. And again, this has a lot of this has to do with the code loading. Why we're doing that. That's, for example, I haven't said it here, but that's why we don't have static type checking, because that would severely affect how, if you want to do dynamic code handling and want to load things while the system is running. Because then you couldn't change the types of anything or add new types or something like this. Then it just doesn't work. So there's a lot of these things that feed back into where we came from as well. But yeah, we just fake things, right? So yes, do people know this about the schedulers and memory management and stuff internally? Is this something generally known? Well, I'll take it. If you've heard it all, just tell me and I'll stop. Okay. So inside the Beam, there's a concept called schedulers, of a scheduler, right? And What it's used for, what its main use for is to be able to spread the thing, the Erlang, when you're running one Erlang node over multi-core or multi-processors. So it's for multi-core handling as well. So what happens is when you start up the Erlang system, by default, it will go and find all the cores you have, and it will start one Erlang scheduler or Beam scheduler per core, and each one runs in its own VM thread. Okay. So if we'll see later, I'm running 12 cores. I'll be running 12 schedulers when I'm doing this, right? And that's, amongst other things, it's used for load balancing. So what's built into the Beam is that it can check the load over the schedulers, because they're running, and again they're running on separate threads and so on, and it can move processes, Erlang processes, between the schedulers to try and keep the load balanced. And there are a number of ways it does it. The lowest, the simplest level is something that's called process stealing. So each schedule, each schedule, it's sort of a semi-autonomous little beam. Right? It's not that it tries to do as much as possible on its own, but it's designed to work with all the other schedulers, and so that they do interact with each other all the time, of course, because you might be sending things across, and you don't, in your code, you don't notice any of this. Right? You can't control it either, for that matter. But what happens is, so if a schedule is running there, and it's got its own little run queue, and it's got its own memory management and things like this for it. It has a set of processes it keeps track of and runs and things like this and reschedules, etc., etc. And what happens is, if a schedule's got nothing to do, say all the processes it has are suspended waiting, it'll go out and try and steal a process from another schedule. So I'll look at the schedules around it and try and find another schedule which has some processes on its run queue, and try and steal it across to itself and run it there. So I'll move the process across. And all the schedulers are doing this, trying to steal things around. So processes are moving around in schedulers to try and keep the load balance as even as possible for the whole thing. And again, this is just built into the system. It's nothing you control. Well, it's nothing you have to control. You can control how eager it's going to do it, or how non-eager it's going to do it, and things like this. It also works the other way. So if it finds you've got, say, my 12 cores, my 12 schedules, they're doing so little work that I don't need all these, it will try and shut down some schedulers, move processes away from them, so schedulers got nothing to do. So we're running on a fewer schedulers than we need to, than we have access to, because that's usually, if you don't make it two. If you don't put too much load on them, it's generally more efficient memory handling and stuff like this. So it does that at the same time as well too. And so it sits there trying to spread the load, and sometimes we'll start compacting the load. And it just does it when you're running. So it's nothing you have to worry about or think about or something like this to do this for at all, which is nice, right? Yeah, it's popping up, fixing my screen a little bit. Doesn't do that. Yeah, it is. Oh yeah, can see more people. Okay, great. So yeah, that is just doing as it works, right? It also in the schedules we have this support for non-blocking. So one of the features of the language is that, or features of the Beam, well, the Beam and the languages, it's practically impossible to block the Beam. Okay, so it's like an operating system. You're running your typical operating system. You might have processes in the operating system that are doing extreme lot of work, but they will not block the other things in the system. Okay, the system might slow down a bit, of course, but it won't block other things. I don't have to think about that. It's exactly the same thing in the Beam. So even if I have a process that's sitting in a tight loop, going chung, 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 and that will be running on one scheduler, that will not block that scheduler. Because what happens is, after a certain number of function calls, which by default now is 4,000 function calls, that scheduler will reschedule that process and put it at the end of the run queue and take the next thing in its run queue. Again, this is not a very complex operation, but it's just something that's built in there the whole time. So this is going on all the time in the system, doing this. And this, again, is something I don't have to think about because the system just does it. Excuse me. You can have some control how much effort it's going to put into doing it, but that's about it. So you have all this stuff going on both to make sure that the load is balanced as evenly as possible across the machine, that things don't block it and stuff like this as well. And this is just baked into the virtual machine. It's quite fantastic, really. So just a quick push here. I mean, you noticed if you look at the language, the Erlang language has evolved very slowly. I mean, we took, what, 5 or 10 years to get maps and things like this for it. So the language itself is evolving very slowly. It is, but very slowly for it. And the same thing with the base OTP libraries. They come new ones occasionally and changes, but it's very slow. There's a reason for this. This is just because we just want to, we don't want to have to worry about backward incompatibility and stuff like this. But yeah, but what is happening is that the virtual machine is being developed all the time. That's getting better, continually getting better internally. And sometimes the things you don't see when you're writing your code, it just works faster, just works better for it. So all these type of things are in there. I mean, I don't know who's been following what's coming on version 24 that's coming soon. Yeah, some people have. The asymptotes, they are really something. So I'll see if I can find the reference to a paper describing the history of this, but there's been work over the last 10 years of doing JIT compilation, of course, to try and make it go faster. And there's the hype which does that for some specific machines. But what they've done now is, I think it was an idea of my colleague of mine, Lukas Larsson, they flipped it. So instead of trying to generate assembler code in the compiler just generates a standard beam like it does all the time. It's a standard beam you can run anywhere. But what can happen is if you're running a new implementation on a right machine, when it loads the code in, it will translate the beam code to local assembler code. So it doesn't do it when you're compiling it, you're doing it when you're loading it. And that's fantastic, because it also means when I'm compiling my code, I can just compile my code and get my normal beam files and run them everywhere and don't have to think about it. But if I'm running on my machine, I load a beam file in, it will compile it down and generate assembler code for me. And that can get a speed up of 4 or 5, 10 times sometimes for it. And the fun thing is one, the code does not become much bigger. I think they found a code size increase about 10%, which is very small for doing things like this. I mean, this is one of the reasons why the original beam couldn't be done, because the C code was so much bigger and they didn't have much memory in those days in systems, so they had to get away from that. But here, it's sort of 10% increase in code, right? And again, when I'm compiling, I don't have to worry about if I'm compiling for my machine or another machine. I just generate my normal beam code, and at load time, if the machine does it, it will convert it. If it doesn't, we'll just run it anyway. It's really a fantastic system. It's both simple and complex, but the idea, the simple idea is just very nice, right? And that is truly fantastic. It's coming in 24. They've been working on that. So that is really, I mean, they're getting really significant speed increases from they doing that. Yeah, sorry, okay, wandered off a bit. But yeah, so what dirty schedulers are here, this load balancing and stuff, that works by running Erlang code and counting for function calls, and after 4,000 function calls, you just reschedule the process, etc. This also baked in the fact there are no internal loops in the system. If I'm looping, I'm doing looping through function calls. So even if I try to have some form of for loop, I'm still doing function calls, so I can't get around that. And do the non-blocking for that. And also there are other things, I don't know if these are things that are just there, but you don't always think about them. But if you look at a typical Erlang or Elixir system, if you look at that, most of the processes just sitting there doing nothing. And they'll be sitting there, they'll wait for a message, they'll get a message, they'll process that message and maybe do some stuff. Then when they're done, they'll sit and wait for the next message, next request that comes in. And most processes are doing that. That's what they're doing internally. But that means you have a lot of processes just sitting there, right? And the way it works now is a process that's sitting waiting for a message doesn't cost anything. It doesn't cost any CPU time. It's just sitting there. And when a message arrives at it, then it's put on the run queue, and when its turn comes, it'll be run. So it doesn't cost it. Again, that's just another feature of the machine internally to support the non-blocking for it. There are other things as well too. We can talk memory management later, but yeah. What the dirty schedulers are, this works fine for threads running or schedules running Erlang code, but if you want to run your C code, you can't do that. So it also has a set of dirty schedulers. So you can when you write your NIFs and also some of the BIFs as well, they run on dirty schedulers, which will just use the operating system for doing that, for working things. That again, just to get around the fact you don't want to block on the Erlang code. A typical case is I'm doing a file operation. Now, file operation is relatively slow compared to running running beam instructions for it. And I don't want to sit and wait for milliseconds when I'm running things that can take micro or nanoseconds to work which way. So instead of sitting that process, that scheduler sits there waiting, it will hand off, say, the file operation to a dirty scheduler, and it'll go on and do other Erlang's things in the meantime. And when the reply comes back, then it'll reschedule that process and continues. There's a lot of stuff going on here to make it go fast, right? Not to block. And there's memory types. There's so many different types of memory. Unfortunately, I cannot get any good slides for this, I'm afraid. But there are different types of memories. There are different memory properties, different types of garbage collections. Some are layered, for example. So if you've got process heaps, each process has its own heap. Instead of allocating each heap from the memory, from the operating system, we allocate a big chunk of memory. Then the internal memory management in the beam handing those out to processes, which means we avoid blocking and synchronization and all these type of things. The atom table is one everyone knows. It's a fixed size table. You fill it, you crash the system. So that's avoid code that dynamically creates atoms in an uncontrolled way, because you will crash the system. It takes about half a second. I have to show you this. This is just too fantastic. Sorry. Let's see if we get out of this, and I'll find one here, and we'll start up another shell, and we'll do to P to. Sure, I will see if I do LS. I'll see if I've got my atoms somewhere. Yeah, we'll go down to CA. So here I've got a little my atoms module here. Wait a minute, I'll make this whole thing a bit bigger so we can see it. I should make that a bit bigger as well too. So we have a very simple little module here. I'll just cat it that here, and we'll just cat it. So we do cat atoms.l. And this just sits in a loop. I call the create function with a number. It does an integer to list and then builds a name with $, that in front of it. And then it creates that, it does list to atom for that, and then just sits and loops. Okay. So if I start with 1, it'll build the atom $1, $2, $3, $3, 4, etc. for it. If I run this, so we're running it all here, and if I just do compile it to make sure it's got the latest versions, we're compiling atoms. Yeah, this is the compiler telling me I'm not going to use that list to atoms call, which is perfectly correct, but it's there. So yeah, I do atoms, create, and spelled correctly as well too, yes. 1, and we do that, and it takes about half a second, including writing out a crash dump. That's how long time it took to fill the atom table of over 1 million atoms, right? And there's no way around this. Have you looked at crash dumps? Oh God, what do people do? So this is the crash dump that was created from when the system dumped. And a lot of information here is very, very internal, but it's fantastic to try and keep track of it. The interesting one is the third line, what's called the slogan here. That just says no more index entries in the atom table. We maxed it. In that half second, we created over 1 million atoms and dumped the crash dump at the same time. That's how fast it is to fill it. And there's just no way around it. And if we go down to the end, I say if we do /, I know I've been here before, so E equals atom. So further down here, we see a list of all the atoms. And these are a bunch of all the atoms we created. And this is the last one we could create before we ran out of memory space in the atoms. So I just go down there, they're all down here. At the end, we've got all the real atoms. But if we go up a bit, let's see if we go. Let's see if I can do that. If we do nope. Let's see if we do junk. So we'll do $0, see if that finds one. Nope, it didn't work. Oh, well, up around here, we'll find all of the atoms. I mean, you'll never create 1 million atoms in your code, but if you do it dynamically, that's how long time it goes. And there's no way around that, because once the atom table fills, it crashes. There's just nothing you can do about it, okay? It just does it. Yeah. You can make a bigger atom table, and it'll just take a longer time to fill it. But yeah, there's a large binary space. I don't know. So what typically happens in process heaps, each process has its own heap, which it manages by itself, and you garbage collect just that heap. And they're generally small, which means the garbage collection times are short, which means they're hardly noticeable. But what happens if you're large binaries? I mean, you're doing video streaming and you're sending megabyte binaries across. You don't want to put those in the process heap and copy those every time, because that would completely crash load the system. So what we do then is there's a large binary space where we put all large binaries, large in this case bigger than 64 bytes, and you just pass references to them, which means you can have codes that sends large binaries between processes, and you're not copying it for it. There are a few problems that with garbage collecting them, because you can't remove them until every process, you know that every process has seen that binary no longer as a reference to it. That's why it's called the RefC memory, because it's a reference counting. So you reference count how many processes are referencing that binary. And that can also create problems as well. The classical bad case is I'm getting a megabyte binary, and I want to have 25 bytes in the middle. They're the ones I'm interested in. The rest I'll just pass on. I don't care about those. So if I'm not careful and extract those, I'll have a reference to those by referencing the whole big binary and saying where I want my 25 bytes, which means I'll never lose the reference. The big binary can't be garbage collected. And there's actually a copy. That's the only copy instruction I've found in the whole machine, is a binary : copy, which makes a copy of it, make sure it's not in the RefC memory. They've fixed that up now, so if you're doing matching, that automatically handles, because that's the problem. That can crash it. We have ETS tables, yeah, they're just separate, they're great, but there's copying because they're outside the process heaps. Every time you're accessing those, you're copying data backwards and forwards. But something, and we've got the process heaps and the garbage collection in the process heaps and stuff like this as well too. But yeah, this is a real picture. It's actually me at work. Okay, we're early 90s here, so we were going to show Erlang at a trade show for it, and we wanted something to attract people. And this little thing you see here, I don't know if you can see that there, that thing in the middle there at the back, that is the small exchange we had in our lab to test all our stuff with, right? And it's got a little red light which goes on when you turn it, but that was not going to attract people. Okay, so we thought, how can we attract people? And we decided, okay, we'd have a little train set, and we would control the train set by Erlang. And this is what I'm working on here. So here I have different ideas for it, and we're running a mad clean train. And even those days, even 30 years ago, you could control them from your computer by sending bytes, control it by sending bytes to it. So yeah, we did this, and we had sensors in, so you could detect where the local trains were and things like this, and keep track of it. And we had, I went slightly overboard. I wrote an ATC system for this, automatic train control system. So you could split up your track into blocks, and you could book a train, could book a path of blocks through the system, and the ATC system would make sure that even when blocks overlap between trains, they wouldn't crash because one train would stop. It's all these type of things. It was really fantastic. I had a lot of fun. Burnt holes in my desk because I realized well, I mean, typically in those days you press the button and the switch would go click and change. Okay, what I hadn't realized was that was both pressing it down to turn the current on, then you lift it up and turn the current off. And there were two commands you had to send to it if you're doing this from the computer. So I just sent the change command, but not the turn off one. So, but yeah. So my desk got black marks everywhere for it. It worked. It worked. It was a lot of fun actually, and it worked in Iran as well too. Then I had a colleague who did a sort of a little DSL for controlling it. I had written a very simple one, but he wrote a lighter one. Another one did a graphical display, so you could see the track and you could see which blocks were allocated by different trains and where the trains were and everything like this. It was really a lot of fun. But yeah. But anyway, so that's work. But yes. Yeah, so this gets us to the ecosystem, right? I think this picture of the ecosystem is a bit old. I don't know if we have a new one anymore. Have you seen anything else, Oliver? I know we've got the EF, the Erlang Ecosystem Foundation, which is doing well, but I don't know if they have a nice picture of it. But this is something we had a couple of years ago for working with the ecosystem. And the whole goal is
LASP to be on there.
Sorry.
I said I want LASP to be on the updated version.
Yeah, there are other things we want as well too. This is a bit old, but I couldn't find another one. I don't know what they're going to do if they have one, right? Have trees in their website, but yes, I don't know. But the whole idea was here that at the bottom you have the beam and you're running Erlang OTP on the top of that. Then you have a number of other languages running on top of this, right? So of course we have Erlang, we have Lxd, we have Lfe, Prologue's my erlog. I'll talk a bit about that later. And luerl is the luerl. Joxa was another language running. There are other languages today running on top of it. But that's the whole basic idea. You have this ecosystem where all the languages are running together, right? And they're running on top of this. So in that sense, they're more or less compatible with each other and they can interact. And the idea is if these languages implementations follow the set of rules, they can interact and support the other ones, which means you can get a system which is better in the whole respect than each language in itself. Right? That's the whole goal behind it. I mean, this is nothing strange here. I mean, this is how Lxd and Erlang work together. They're running on top, and well, they both compile down to Erlang, but they interact with each other and things like this for it. And as long as you follow the rules, the same set of standards for things, they work. It's not always easy to do it, but that's how it works. Right? And this is the whole idea of the ecosystem. Okay, what you want to do this for. And yeah, extending the system here. There's just different ways of extending the system for it. By the way, that is a Leonard Cohen CD. And if you haven't heard it, it's fantastic. It's old. It's old. It's full of typically depressing Leonard Cohen music, right? But it's extremely good. And if you're not nice, I'll play it. But yes, I plan to be. Yeah. So it's a fantastic CD for it. New skin for the old ceremony, yes. And so the way I view it, this is sort of my personal view here, is very much I've got two ways of different ways of implementing languages on top of the beam, on top of Erlang and the beam. One I call native languages. Now, they're the ones who've basically kept the same semantics as Erlang. Because as I mentioned, Erlang and the beam are very, very closely integrated with each other. The beam is designed to run Erlang. Literally, that's what it's designed to do. So all the support, everything it has in it fits into Erlang like this, right? That's why I can just do these things so easily. That means if you want to run a language efficiently on top of the beam, it has to basically be compatible with Erlang. Okay, that's just the way it is, and that's what I call native languages, because they're made to run on this system for it. And they might have different syntax and different packaging, but at the bottom level, they're Erlang. And of course, that's if you look at Lxd, I don't know, I think a lot of you are using Lxd. If you look at that, it's the semantics of the bottom layer for it. It's the same as Erlang. And this is nothing strange. This is what it's designed to do, right? Designed to be like this, but that's how it works. And that means it can run very as efficiently as is possible on top of the beam, because it's doing that level. Okay. And we've got Lfe, my lisp-flavored-erlang here. Effiana was another attempt to do a language. Clojure was a Clojure-inspired implementation on top of it. I think they still exist. There are a number of statically typed languages that are coming now on top as well. Statically typed functional languages, which can introduce new features, new types, or simulate new types, and things like this for it. They're coming as well. But at the bottom level, they have the same semantics, so they can interact. That's what I mean by native languages for it. And of course, what happens there is how these work is that you have the beam at the bottom down here. I cannot get a color here, I'm afraid, on my pointer, I don't think. Can I? Annotate, pump. No, I have to be careful, because if I start doing that, I might start drawing stuff. No, I don't see anything. Mouse, what happens? Oh, well, no, I can't do that, I'm afraid. Well, if I can, I don't know how to do it. Anyway, yeah. So what happens, you've got the beam at the bottom here, and you've got Erlang on top, and then you have OTP. And your new language, that ends up generally being on top of Erlang, sort of beside OTP, and it will have a bunch of its own new libraries, which will be run on top of it, and on top of OTP, and on top of Erlang. This is exactly how Elixir works, right? And this is fine. This is nothing strange doing this. This is what you end up doing if you want to run a language I call efficiently, I call natively on top. So if you start looking at Elixir at the bottom level, it's exactly the same as Erlang, the same semantics and everything like this for it, same data types, of course, and which means it just runs very efficiently on top of the bit. Okay. And that means they can make full use of Erlang and the OTP libraries, which of course Elixir does. They've extended, of course, but they use it based on top of the existing ones. And that's Elixir, right? You see this. Dynamic functional language designed for building scalable and maintainable applications. Yes, of course. Right? And it's influenced by Ruby, yes, but it's very important to note here. If you look at the Elixir team here, they're very explicit in saying it's not Ruby. Okay, because Ruby has different semantics, and then you could not implement it as efficiently. You could do it. It's not impossible to do it. That's not the issue. But if you want to get the same type of speed up on it, the same speed, then it has to be that. And that's why it's Ruby influenced, but it's not Ruby. And that's why if you try and write Ruby code on it, it's either not going to work or going to behave very strangely, because that's not what it's designed to do. It's got metaprogramming capabilities using macros, yes. It's got a lot of libraries and interfaces. They've been standardized, rewritten, and extended, yes. That's one of the things I'm slightly jealous about Elixir. One of the things when we were developing Erlang, seeing as the whole thing was iteratively being developed, we're getting new things coming in and things like this for that. Some things that came into the language, they might have been doing the right thing, but they mightn't have looked very nice. But once they were in, it was very difficult to change things. Because this happened a number of times. People complained about the libraries. Our libraries are terrible. The naming's terrible. The argument ordering is different and everything like this. And they're perfectly true. So some libraries, you'll find the thing being worked on as the first argument. Some libraries, it's the second argument. Sometimes it's in the middle. And the naming conventions don't exist and stuff like this. And they're perfectly correct about this. But we said, okay, we'll change them. We'll redo the libraries. Then people start screaming even more and say, no, you can't do that because they'll break our code. So that's one of the things we're stuck with, right, in the Erlang side. Unfortunately for Elixir, they could think a bit more when they were doing this, because they weren't evolving the language in the same way, so they could make a lot of standards in the libraries, standardize things for it. I mean, for example, if you're running Elixir, you'll find the thing you're working on is always the first argument. I have not found a case where it isn't, right? Again, that is by design. We say, we're going to make it the first argument. We do that, that's fine. That's good. That's some of the things, we could not do that, I'm afraid. And yeah, so it's set of build tools and packages. Yes, the mix tool came extremely early. That also shows a cultural difference between the Erlang and the Elixir side. I mean, in Erlang, we took, 15 years before we got rebar or something like this, more. It just wasn't in that type of systems we were developing, that type of companies and programs that expected to have it. Whereas if you come into the Elixir, people the Elixir were initially looking at, they were very much expected these type of things. So they came very clear, very early on. But yeah, that's just how it works, how the culture and things work. But it's got the same basic semantics. It's got the same style modules and functions. I mean, Elixir modules work exactly the same as Erlang modules when you reload them and what you can put in them and things like this for it. You can put a function in a module, that's basically it, right? And the same thing with functions, that you can have a function cannot have a variable number of arguments, it has a fixed number of arguments, but I can have different functions, the same name with different arguments and different functions. That's just baked into the system.
But also Elixir taught Erlang to put help documentation in the module. Yeah, I'm actually slightly ambivalent with that, both yes and no. It's nice. If you're sitting in, for example, in the shell and you want to say, what does this function do? So you do help on it or H on it and get the function back. The problem I found with the Elixir one is sometimes you can get about 5 pages of code or documentation, which makes it very difficult to read when you're sitting in the shell. And I'm not complaining about the documentation is bad or anything. That's not what I'm saying. It's just that sometimes I want a lot of documentation and sometimes I just want a few lines. If I'm sitting in the shell, I want the short bit, but when I want the long bit, I want to go out into my browser and read it. That's why I want to see the long bits, right? Yeah, that's
my main complaint about the documentation, including the documentation in the modules. Yes, but Erlang's got that now, and that's great. I've done this. I mean, I've incorporated that into LFE as well too, because it's nice, right? But yeah, that's just my personal. So I want to see something. I want to do help on a module. I want to see about 5 or 10 lines describing what this module basically does. And I can do a function. I'll see a few lines and maybe the input, the arguments for it, and that's about it, right? And if I want to read a lot about the documentation, I'll want to go look in my browser. And that's what I want to see. But yeah, that's one of the things that we've inherited from the Elixir side as well too. I think they've influenced the build tool, writing build tools as well, indirectly at least anyway. And now in the ecosystem foundation, the EF there, there's a lot of work trying to integrate these, get better integration between the languages now. So I think doing work on how I can build when I'm building using Erlang, the rebar, how I can build Elixir stuff, and when I'm using Elixir mix, how I can better build things using rebar on the Erlang side. You just get this interoperability much better. Now I think in the long run will benefit everyone for it. But it also means because it's got the same semantics, every new feature that comes into the Beam, Elixir sees it, of course. If we're adding things in the libraries, Elixir sees them because it's just there. But the intent here is not to stop other languages building things on top of it. I mean, Elixir's got a big bunch of its own libraries. That's fine, right? Because they just want that. It's added its own behaviors because OTP allows. The OTP is not, I mean, it's got original Erlang OTP comes with 5 behaviors, right? The 5.1, its application supervisors, gen servers, gen state, and events. They're the 5 ones. But Elixir, I think, has added at least 2 agents and tasks for it. That's fine because the system is not locked in any way to these 5. So you can add new ones. That's great. Do that, and you find something you'll think your users have a need of. Well, add it. Do that for it as well. But the bottom level is the same thing. And this was just saying before, you can't add new data types. The system will just will not allow it. You can't do it. You fake it. And as I said, Erlang fakes it using records. Elixir fakes it using structs. Erlang records are built on top of tuples, tag tuples. Elixir structs, they're tag maps, right? We don't have strings. Erlang uses list strings. Elixir uses binary strings, and they're just the same thing. I don't know if you tried this. Let's see if we go out here.
That also means that you can just use binary or termed binary for some really nice integration with other things. We do that to use Python from Erlang all the time and just let it return BERT.
Yeah, no, I just want to say that this, I mean, I can do something like this, ABC, oh, sorry, right like this, ABC, something like this, and I'll print it out and I can do something weird, like I can add something like this, and that works fine. Whoops, we want that one, and that works fine as well, right? But what I've actually done here is I've actually written, so I know these numbers, so that's easy. 97, 98, 99, like this. I create this binary, and it's the same as the string ABC. And if I could remember this, if we do this, let's see. We'll put that one there. And now, sorry, I have to go a bit Erlang-y here, but never mind. Erlang colon binary list. Oh, yeah, because this is, we're in Elixir now. We get back. Sorry, that's a dot. Finally, that's the binary. They're the bytes inside the binary, right? And if I do this, if I do x equals this, which I can do, and then I do Erlang colon Erlang dot Erlang list to binary. Binary of x, I'll get back the string. So I can write this, for example, if I can get the string back in again, we'll see if I can do this. No, that's one. right, like that. And I get exactly the same thing. What am I going to do now? Wait, sorry. List to binary of X. My point is just here that they're exactly the same thing. And what happens is that when the Elixir system prints out a binary, it checks, can this binary be interpreted as UTF-8 encoded characters? And if so, it prints it out as a string. If it can't, it prints it out as a binary character form. So this is nothing strange, but I'm just showing that we don't actually have any types inside. And the same thing with a struct, it's just a map. And there's no way around this. This is not Elixir doing anything wrong in any way. It's just that this is just how it works in the system. And because we have the dynamic code handling, means that it's very difficult to allow defining new types in part of the system which aren't the same everywhere. So this just can happen. There's just no way around that. You make choices. Erlang made some choices. Elixir made some other choices. They've got this as well. Yeah. So another one is lisp-flavored-erlang. This is my baby. So Lisp was actually my first high-level language, and I've missed the parentheses for many years coding the Erlang side for it. So when the time came around, I made a Lisp-based front end for it. So it's a Lisp syntax front end to it. It's a real Lisp, so it's got all the things you want in Lisp. It is truly homoiconic, and it's got Lisp macros. I mean, macros the way God intended. It's fantastic. Everything works there. But one of the things here was I decided that I wanted an efficient implementation, and standard Lisps, say Common Lisp and Scheme, they do things differently from Erlang. They have mutable data, for example, which we don't have. They have a different way of handling code. They don't have modules in the same way. They have packages and things like this where you can other things inside a package. I don't know if you've thought of it, but the only thing you can put in a module are functions. That's a module is a collection of functions. If you look at, say, Common Lisp packages, you can have variables that have variables in there with variable bindings and stuff like this. Well, you just can't do that. So that means that to make it efficient, I had to adapt the Lisp to fit on top of Erlang. So it's no mutable data. I only have the standard Erlang data types, yes, and Erlang style modules and functions. I mean, Lisp has the feature you can have functions with variable number of arguments. You can't do that on the Beam. So it doesn't do it. Macros are only compile time. I don't know if you run Lisp, but in Lisp I can define something that looks like a function. It's a macro. It does and the system will, when I call it, will say, "Oh, this is a macro." And we'll do macro expansion for it. I can't do that. The Erlang system does not support that, and it's a Lisp 2 instead of Lisp 1. Unless you're a Lisp hacker, I'm not going to get into this. But yeah, so here are other languages as well. Here are a couple of ones that are statically typed languages that now work for. We've got the Gleam and we've got Caramel. There are different ones doing, and they're just attacking the problem of putting a statically typed functional language on top of the Beam Erlang system. That's it. And they work fine internally. They can work fine internally. I haven't played with these, but it can be difficult to interface other things, especially if you want to send messages. I know that for a while, WhatsApp were looking at doing a statically typed Erlang, called Erlang 2. On top of that, they shelved that for the time being, but they have exactly the same problem doing that. This functional side wasn't too difficult. I mean, you had to decide what you wanted, of course, but interfacing and sending messages, that makes it very hard to type things for, at least statically type things. So yeah, that's that. Okay, so they're the ones I call natively. Now we've got the non-native languages, and they're the ones I've also been playing with here. There, the thing is that you want to implement a language which does not have the same Erlang semantics, but you want to keep those semantics of that language. So you might want, well, I've implemented Lua, but you might want to implement Python. Say I want to implement Python running on top of Erlang inside Erlang. I could do that. It's not impossible to do it. I'm not going to get an efficient implementation, but it's perfectly doable to do that. So you just have to decide when you're implementing it, when you want doing a new language. I like doing the languages are fun, right? But you have to just decide where you want to go and what am I willing to pay for it. Right? So if you want something that runs very fast, it becomes Erlang compatible. If you want something with different properties which aren't Erlang compatible, then you have to pay for it. And I made the decisions here for it. I've got Lua. Lua is a nice little imperative language. It's got shared mutable global data, everything we don't do. It has completely different handling of code. Lots of things like this. I think I'm getting chats up here. Or, let's see where I was. Yeah, thinking forth. I haven't implemented a fourth on top of Erlang. I implemented a fourth in VAX VMS assembler, but not on top of Erlang. That'd be quite fun to do that, actually. Again, you can do it, but you still have exactly the same problem. It does completely different memory handling. Fourth's nice. I don't know how many people have played with Forth. It's a very nice little language. What's fantastic about it, the actual base Forth implementation is small. Right. So I found a book on it, and I wrote a small one in assembler, and the assembler is quite small code. With that, you can implement Forth and implement everything on top of that in Forth. Right? It works. Right? That was the most remarkable thing about it. The core is tiny. In many ways, it's a very simple language in that sense. But yeah, so luerl, I did Prologue, erlog as well too, because again, I wanted that. So this is a bit more where we end up now. So
what have you used erlog for?
I haven't used it for anything. I did it as an experiment. I don't know if anyone else has done. There was one guy many years ago who was working with it. He did his own fork, and he started using ETS data for creating large databases. I did not do that because I'll get to why I didn't. But yeah, I don't know if he did anything with it. He did a fork on it. He did quite a lot of work on that. So I think he was actually going somewhere with it, but I can't remember what happened with that.
I have a project that I should have built on top of it, but I didn't know that until about 18 months later.
It's fine, right? Well, I'll get to it soon, but yeah, so I think yes, that's it. So yeah, so for it again. So Lua, I don't know how many people play with Lua. If you're in the gaming world, you probably have. It's great. It's a nice little language. A powerful, efficient, lightweight, embeddable scripting language. Supports procedural programming, object-oriented programming, functional programming, data-driven programming, and data description. I think it can basically handle anything, right? It's a simple language. What I think is fantastic about it. Yeah, I've tried writing Prologue interpreter in Lisp as well, Randy. That's fine. But yes, it's Brazilian. Lua is Brazilian. It's a tiny language if you start looking at it. And what I think is most impressive is they've kept it tiny. So they managed to get the right set of primitives in there. So I mean, the only data type you have for building structures are key value tables. They do everything with key value tables. So if you have a key value table where the keys are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's an array. And do other things as well for it. So that's the only data structure they have. They have meta tables coupled to it. With that, you can, again, very simple mechanism, very straightforward. With that, you can suddenly do inheritance, class inheritance, things like this for as well too, working with that. So it's a very simple, nice little language, and they managed to keep it simple, which I find very impressive. So the first implementation I did was for Lua 5.2. And I've done almost everything. Then came 5.3. And the biggest change between 5.2 and 5.3 is they added integers. So in the older versions of Lua, you just had floating point numbers. Then they added integers into 5.3. That was the biggest change. I mean, this is the level we're talking about for it. They've just made it very nice for it. So it's a small imperative language. It's got a few idiosyncrasies in there, but it's okay. It's dynamic. I mean, I can just load code as I go. Code just ends up in my tables. It's lexically scoped. It has mutable environments, which are a bit strange. So if I've got a stack of functions like this, And this function, the top level function up here, knows about the ones down here, can change variables in the stack further, values in the stack further down, right? Which makes it a bit tricky to keep track of all those things. And it's a common scripting language in games, both for scripting games and for scripting environments. Yeah. So this is just a little bit of Lua code to see it. We're just this is a very sneaky but cunning way of doing things. What this says here, I'm binding 4 variables A, B, C to 0 to each of them, and there's nothing to end a statement. So if I had happened to forget a 0 here, then what would have happened is the last one, D, would have been bound to nil, and the compiler wouldn't complain to me in any way because it's not a mistake, right? So sometimes it's very easy to get very strange code if you forget things. So if I had written, let's see if I can get my pen working here. This is where it gets really weird sometimes, but yeah. So if I had where are we? Draw. If I had written, let's see if we've got it up here. If I had written this instead, A, and I forgot the comma and wrote B, comma C, comma D equals 0, comma 0, comma 0, like that, that would have been perfectly legal code. It wouldn't complain, but A would have been bound to nil, and B, C, D would have been bound to zeros, and the last one would have been, well, the D would have been bound to both of these, right? That's perfect legal code. So it's very easy, if you're not careful, to make code mistakes like this for it. It doesn't have anything ending statements. So there is a semicolon which you can use to end a statement, but you don't have to. Yeah, so it's fantastic. It's great. So this is what this is doing. We're just making ABC bind that. We're making local inside this script, top level script here. We've got BCD. We're setting that to 1111. So we've got a global BCD and a local BCD, and inside this do statement here, we've got CDs at different levels, right? So we have variable shadowing. It's quite fun, actually. This is not difficult, but it's nice. It's a nice little language, actually, for it. And yeah, let's see over here. Wait, I'm just going to get rid of this one. Now we can do it. Yeah, and so luerl, it implements Lua 5.3. There's nothing strange there. All of it except for one thing. It does not implement coroutines. I could do it, but I didn't bother doing that, seeing I thought that I could use Erlang processes instead. And it does, we implement the shared mutable global data, because this is what Lua requires, right? If it didn't have that, it wouldn't be Lua. So here the design choice I made was, I wanted to implement Lua. Originally, I wanted to implement a statically typed or a dynamic or a mutable language with mutable data, and I didn't want to invent my own language, so I picked one. And first, I was looking at JavaScript, but that was quite big. So then someone recommended Lua, so I looked at that. And the goal was here to implement Lua. So we do have shared mutable global data. Okay, that's just it. And we have Lua handling of code, which is very different from the Erlang handling of code. Lua doesn't have a concept of modules. I can create a function, just clip it straight into any table I want to there. And I can add and remove them and things like this as we go. It's a completely different way of handling code. It just does not map onto Erlang the way Erlang does it at all, right? And there are other things in there as well, but it's a very nice little language. So where you end up in is that you have to, so you've got your Erlang down the bottom here, and you've got the Lua in top here. The implementation, it has to be a layer handling data. Okay. Amongst other things, you've got a little virtual machine, so you've got to compile it down to a virtual machine. That's fine. That's not too bad. Again, there are a few trickies there, but it's not too bad. But the thing is, for handling data, I have to put a layer between Lua at the top and Erlang at the bottom, which handles that for me. So I have my shared global mutable data, which means if I have a table and I can pass that into one function, it can modify it, and I pass it into another function, it will see the modifications. That's just the way it works, right? We can't do anything about that. So yeah, so we have to keep track of the tables. We have a table of tables. We have a table of environments, the call stack environments. We have a table of user data. So you can put user data in there as well too, and for it. And we have a table of functions. And this is the global table. We have current, stack, and meter. And each of these tables is implemented, so it's got the actual data, which is usually a map. But we want to be able to garbage collect it and reclaim the data. So we have to keep track of which ones are in use, and we free them. And I didn't want to make a new integer index every time, because then you eventually run up to millions, right? So when you go through and you need to do a garbage collector, which garbage collects the Lxd data, the Lua data. And then when something gets free here, it's just that index is put on the free list. And the next one is, when we use that, we keep reusing these. So we don't bump up the indexes all the time, right? We just have the ones we do. So we have to do garbage collection. When we decide to do garbage collection, we have to step through what we're running at the moment, follow all the pointers of that into the tables, follow all the pointers in the table to reference other tables. You can have circular references, of course, looking at code and following what's in the code, and then mark everything as being in use, and then go running through and garbage collecting everything which is not in use. Then we can pass everything across the Erlang garbage collector, will reclaim the data. But this has to be done in here just to get this right handling of memory for it. You have the mutable data and it's shared, right? And it's global and it's shared. So I can go in my global table, and there's a big tree of tables that has in there, and I can change things down in one of those tables, and someone else will see those changes as well too, because that's just how it works. So we don't have any local data, and that's one big layer you have to put in between to do that, right? And that's just something you have to pay for to get that type of memory handling. That's all there is to it, and it's a choice. You make a choice to do this or not. This is one of the things I want to do here. And I've got some code. Well, this is just meta tables. You can have meta tables inside a table. So here, for example, is a table. This is a record of a table. It's got the array bit here. This is the key values bit. We have, well, there are two, that's split up into two things. And here we have the meta table for it as well, if we want to bang that meta table. So the thing is that it has a set of operations that work on integers integers for it. And I found it was easy to split a table up into two parts. One part where the keys are integers, and the other part where the keys are anything else. And that's what the A and the D is. This is the dictionary bit, and this is the array bit here. It means, for example, there are instructions and functions, libraries for stepping over array indices. It's much easier to keep them separate to do that. It makes the code a bit more complex, but it makes it easier to work with it. It makes it a bit faster too. So if in a table I'm referencing a table, I have a T reference here to the table. And this is the index of that thing in the table, so to speak, in this table data here. So when I'm referencing the table, I have to go in and I have to find the main data structure, find the data inside the tabs here, and look at that index and find it. So everything's indirectly referenced. There are no direct references to things. It's the same thing with the user data as well. So you have a reference to things, and you have, well, here's what it looks like. These are environment references. We've got the user data references. We can have metadata and user data as well too. It's quite fun. User data is data which the Lua system does not see. If we're running on the standard C implementation, that will just be a pointer to something else somewhere else, right? But we have exactly the same thing here. We have threads, although I don't use that. So we have this layer of putting this layer of stuff in the middle, right, for doing this. Wait, we can do this. Did I do this? No, sorry. 1 second. Where did I put this? Here are some things I forgot to bring up. And I will do that. This is a keynote presentation, and one of the things I've found with keynote presentations, you have to be very careful running those on the screen, because they tend to, even if running multiple screens, they tend to grab both screens, right? So what I was looking at, these are the ones I'll just do this, and I'll do that, and this is the Erlang side for it, yeah, or the log side. We'll do that. We'll put those in there. Sorry, we'll unskip those, and then we'll generate a new C file like this. Sorry about this, guys. We will export to PDF. and then we do that, and we do next, and we write it out there, we put it there in the 2021. No, we will put that in, where do we want to put this? I'll just put on my drive. Structs TV. I'll put it down here. I don't know if it's a good place to open this. We'll do this. And export. Oh wait, sorry, I can put it there. I can put it somewhere else better. I can put it in the downloads, of course. Now I see better here, and we'll put that in the downloads, and I'll do export, and I'll overwrite it. Do that as well. And now it should work. Let's see. Okay. Let's see if this one works. And then Zoom has this thing of it wants to keep itself on top everywhere, which is slightly irritating. Excuse me a moment. Let's see if we can get this. We'll keep it better now. Yeah, it should be that one, and we'll see if this is better. Place it. I'll see if this works any better now. Yeah. This will be the same. I actually had some code somewhere for working with these things, but layering that. Yeah. Which unfortunately did not get included. Yeah. I can look a bit afterwards. I can show you some code afterwards, but we'll run through this bit. We'll run through this bit now. So we're back here where we were before, I'm afraid. But I'll show you some of the internal code later, handling these data structures. It becomes a bit complex, but it's not too bad. So that's the luerl. So erlog, that was also, I wanted to implement a Prologue, and it wanted to be standard Prologue, nothing strange, behaving exactly like Prologue does. And it's a subset of standard Prologue. If you go look in the standard Prologue books, you'll see everything erlog does is a subset of that. Yeah. So I'll just get rid of that one. What happened? Let's see. Wait a minute. What do I show? What do I see now? Excuse me one moment. I'm getting a bit confused here. Yeah, this one's okay. This one is okay. So we cancel, and we'll just put it down, we'll edit it, and we'll do okay, we'll save that. Okay. Right, now we're up. So erlog. Unfortunately, I don't have a logo for erlog. If anyone's interested in doing logos, I'm very open to that. So we'll go back to view here. Yeah. Right. So it's standard. There's completely different semantics. It's got backtracking. It's got logical variables, and it's got unification, which is very different for handling things. There's a good mapping between erlog and Erlang data structures, however, which is not surprising, seeing this is basically where Erlang came from, except for logical variables. We don't have logical variables. The problem with logical variables is they change when you backtrack. Right. They can lose their values and get new values and things like this for them. So that in one sense, they're not, doesn't have mutable data, but variables can change values when you backtrack. So what I did was, well, I don't know if you've looked on it, but there's a tokenizer tool called Lx, which is based on Lx and Lfe. It leaks tokens for it. And it's in the same way you define tokens using regular expressions, and then it will define code for parsing, for scanning and generating tokens. And that works fine for doing, for scanning and tokenizing erlog, the Prologue. That works perfectly. That's how, by the way, well, Erlang doesn't use that, but does it the same way. The trouble is, it would have been nice to have a parser generator, something like Yek, to generate the parser. But the trouble with that is that if you start looking into Prologue's semantics of it, you'll find that it actually, the parser is backtracks. So you can get a really weird case. I mean, I can parse forward, bump, 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 and everything works until it gets here, And then the parser says, nope, this is an error. And then it'll start backtracking. And every time I get options, I can go down different paths and start parsing things for it. And this actually happens in the parser. So if you want to make something that's compatible, you need a parser which can do backtracking. Right? So that means you end up with a handwritten parser for it. Right? Because I haven't found a parser generator tool that can do that. They're all very predictable in that sense. That's what they try and do. I mean, you might have look aheads and things like this for it, but you want to have there's one path through the thing. But Prologue backtracks. It's not difficult to write it, but you just have to write it yourself. Yeah. And data structures is great. Prologue atoms are, strange enough, just the same as Erlang atoms. Numbers are numbers, lists are lists. For Prologue structures, we use tuples. That works fine. You have a Prologue structure that looks like this. It's foo with a bar and a 42. I can just replace that with a tuple foo and a bar and a 42 like this. And because Prologue just doesn't have tuples, not by default, not the standard, some do before. So what this means is this is illegal in Prologue. I cannot have a foo that looks like this without any parameters in there. That is illegal. So this data structure is something you'll never get in Prologue. This mapping, because you'll always have at least two elements of a tuple there. Okay, this is just something you'll never do that. So it works fine except for logical variables, and that they're both global in one sense and they're mutable as well too, and they can be unified. And if those haven't worked with unification, it's sort of like pattern matching in both directions, right? Okay, so I mean, typically pattern matching in functional languages goes one way. I've got an expression, I match it against a pattern. In unification, I have two things. Both sides can be values and they can be patterns as well at the same time. So that both can have unbound variables in. They can match and bind variables on both sides in one go. I will show you for doing this, right? Well, I can show you directly. So here let's see where I had it. Somewhere I was running erlog. Where did I do that? Yeah, we're doing it down here. So I'll just get this slightly down and we'll pop it up. So here is some erlog, well, it's Prologue, and here I'm running the erlog system, I think. Nope, that was something else. Where was the other one? Too many windows. There we go. So here I'm running erlog. Here I was just reading, I was just showing. So what I can write in erlog, in Prologue, I can write an expression like this, which is lists of x and the variable like this. So it's a that, and I can unify that against 3 and y. So we see the variables here, they're unbound. We're unifying this, and if I do this, I'll find, yes, x has been bound to 3 and y has been bound to 2. Okay, and that's just how it works. Now I could try I could try backtracking, but there's no more backtracking here. So unification works both ways, and I can do another one. We can make another one as well too. We have to go here. So say we do like this. We do z here, and we put another variable in there. And now z and a are unbound. And now we find that a's got, well, this just shows it's a variable. X is 3, y is 2, and z and a are the same. So Z and A have been unified. And I can't backtrack over that. But if what I can do, say we do another step here, and now I say A equals 42, like this, right? So now this will unify Z and A, and then we'll evaluate that. And now we'll find both Z and A have got the same 42. So they were unified. So A and Z were referencing each other. One of them was being bound. That automatically binds the other one. But yeah, this is quite fantastic, right? And we can do backtracking. So here, for example, we have a family tree here, and I can say, I've loaded this one in here. I've loaded in up here, examples family, and I can, for example, I can backtrack over parent. So I can say, this is Prologue. I can say Bob, and we'll do X here. And what that will, if we look here, we'll see Bob is a parent to Anne. So we'll do that. We get back Anne, and I can do a semicolon, which says backtrack and give me another solution. And I'll find it's backtrack to Pat and things like this for as well. There are no more. And I can do mother. So I can do mother. This will return all the mother relations between X and Y. Okay, so we do that, and we'll find these because a mother is if a mother is if X and Y, for X and Y, if X is a parent of Y and X is female. Okay, this is the definition of mother, right? So we've found one, and I can find others as well too. So there were these two, and I can do fathers and things. So I can do all the backtracking stuff we expect to run from Prologue. This is just basically straight standard Prologue syntax flow. It comes straight out of the book. And we can do other things as well too. So we're implementing all these fun things in here. Right? But this means the variables have to be handled very specially because they don't match Erlang variables in any way. We need to have a data structure representing those. And need to have a data structure which I can see is this is a variable. This is not something else. And what happens is we use that structure because we saw from the previous slide that is not used in any Prologue data representation. So I can use that to represent a variable. And that index is indexed into a global table, which can either, well, depending on how old version you're running, this actually ran on 16 as well. It could be a dict or an array. And when you're building up your stack, you're mutating that, you're changing this data structure the whole time. You're working with this data structure the whole time, containing all the variables and binding things, and you can bind a variable to another variable. And when you backtrack, you go back down the stack and you pop up the old one, so you get the old variable bindings. So you can do this. You have to handle the variable bindings in this way. Faster, efficient Prologue implementations just actually go in and mutate data in a stack, doing the same thing with the stack as well too. But this means you can you go forward. You're building your stack forward until you hit the end. And if you backtrack, you go back down the stack and you get all the old variable bindings and things like this where you are, and you can step over. If you've got choice points, you can see. We'll see some more examples of this later. So yeah, what I want to show here is that we'll make it big again, I think. Yeah. So backtracking is not difficult to do. Okay, this is Erlang code, but the Lxd version being almost exactly the same. So one way of doing this, and this is, we compile it down to Erlang code here, but so we make it, here's our top call. We want to do something with data here, and we always make a continuation. So the continuation here is that the continuation is a fun of one thing. And if that thing was a succeed, that's it. If we hit the end here, we'll return succeed. Well, why we return succeed? We'll return succeed or fail. We'll see in a moment, right? So we want to find the solution of data with this continuation. So how this works is, say we've got A here, and A is going to do stuff, right? So A, it's the thing it's going to do, what the data is going to work on, and here is its continuation. So it evaluates the Erlang function do stuff with data. If that return succeeds, we got the new data, then we just call the continuation with the new data. And if that didn't work, it failed, we return fail. And if we want to do multiple things down here, we'll see in this case, so B does do stuff B, more B stuff B, and even more stuff here. So our data, we first evaluate new stuff B with data here. This is the same thing we're doing in here. We get back our new data, and then we make a continuation which does the last one, the even more stuff B with the continuation we passed in here. And then we do more stuff with the data we got from there, and our next thing we got from here. So we build up a thread of continuations. And we step down we do what we're going to do, and then we do our continuation, which does what it's going to do, and then does its continuation, etc. So we can write this. This is not complex to write and such. We can do choice points. Now we're getting interesting. Though this is just going forward. So why do I want to return succeed, and why do I want to return failure? So here we got something. The C here, it does some stuff, and now we're saying these The semicolons in Prologue, well, the semicolons in Erlang are the same as semicolons in Prologue. They're alternatives. So we're first going to try more stuff 1. If that works, we'll do that. If that fails, we'll try more stuff 2. If that fails, we'll try more stuff 3. If that fails, the whole thing will fail. So we can implement this by doing our stuff here and then doing it, have a set of choice points. Now, a choice point here is a fun with the new data and the next alternatives. So these show all the alternatives. Either we do more stuff 1 and that works, or we do more stuff 2 and that works. And we call the CP function the choice point for that. This is how we implement choice points. So we have goals. Sorry, the data here are goals. So we evaluate that goal, the first one, in this case is the one that. If that returns succeed, we return succeed value. So if that's gone all the way front and succeeded, it might have failed internally there, but it doesn't come back to us and succeed. We succeed. We've done our job. We're ended. However, if that returns a fail, then we call the choice point on the next one. So we test the first one. If that succeeds, we're happy. If that fails, we try the next one. Then we try the next one. And if we hit the end, none of them have succeeded, we return fail and we pass the buck up to the next set of choice points. So this is how we can implement choice points directly in Erlang. And the mapping to this to Lxd is very straightforward. It's just basic syntactic change. So this is how we can do it. This is how we could do it internally, but this does not handle the variable bindings. Okay, the variable binding, if we want to do proper variable bindings, it's getting complex. You can do it by passing variable structures around and having variables, say, in a map, and then roll back to all the versions of this map or whatever. But that's done internally. But Erlang doesn't do it. So by design, so it's impossible to go back, but we explicitly have to do this ourselves in the implementation. And it's efficient, it works, and all solutions is possible as well too. There's implementations, we can do all the solutions and things like this for as well. It's not interruptible, not what we saw before, but not these examples, we can't interrupt things. But if we write an interpreter for it, we can do that and have better control of what's going on while we're working. We can come a bit and say, stop here, and then say, we want to go on and fail, which is exactly what I was doing in the Prologue show. I was getting back a solution and say, yeah, I don't want this one. So I do semicolon, which says, give me another one. And it backtracked, failed and backtracked and got another solution when we're stepping over our parents. So I just want to say finally extending the system. We're talking with external systems. We can have ports to the outside world. That's just basically talking with other processes running on your operating system. Natively implemented functions, we can do C nodes. There's a special case of ports where the other thing behaves from the Erlang point of view as if it was an external, another Erlang node. So you can send messages to it and link things like this for it as well. And when to use, why to choose one over the other. The native language, of course, it's optimal, it's the fastest, it's conceptually easy to interface to Erlang, and it's safe. Safe in the sense that if you get an error in this code, all that'll happen is your Erlang processes will die in the same way Erlang processes normally die, right? So that's what means it's safe. You're not going to crash the system by doing this. It's basically Erlang-like languages. And typically they might need a large environment to be usable. They'll have their own libraries and things like this for it. This is nothing strange. If you're going non-native languages, there's no restrictions on the language. It's good use of the beam. It's fast transfer with Erlang because you basically being called by Erlang, you can call Erlang for it, it's safe. But it's definitely slower than the normal implementation. Right? There's no way around that. And it can be costly to implement it. And you need an environment for this. The global state, the datable, mutable data, etc. I was talking about before. You need all these things as well. Of course, you have to do this. The external systems, I can access anything. I can monitor and manage systems. It's efficient, maximum efficiency. If I want to implement Python, the fastest Python I can do is talk to one already written outside and communicate with that. I could implement Python internally, but that would be slower. This can be either done using ports, or it can be done using NIFs, which is basically calling C code inside the Erlang emulator. And the interface is generally a bit slower, but it's safe. If it's external, running other operating system processes, if they crash, all I will see is I'll get information that they've crashed. If I'm running internally in a BIF and that BIF, the NIF crashes, then I'll crash the whole Erlang system. So it's just a little bit about this. For yeah, I want to. Yeah, any questions so far? I've seen some things for it as well, and apparently I'm sort of running out of time. But yes, but we saw here that I can compile things. I can look after that one. I think we can get rid of him. Yeah. So we had the prologue. Where did that go? We're running this, and here, yeah, this is what I was just saying about the backtracking. If we do the mother again, we see that, okay, I've got, this is the first solution to mother. So we find a parent of XY where X is a female. That's what we're looking here. And we see that, let's see what we got here. We've got Pam and Pat are females. So we see that Pam is a parent of Bob and Pam is a female. And that's why I see Pam and Bob here. Now when I do a semicolon, I'm in the shell saying, now I've got, give me fail and give me another solution. And that will say returns Pat and Jim. And if I do another semicolon, it says fail again and give me another solution. And it says no, because there are no more solutions. I have not looked into Nano. I saw a question here on the chat. No, I haven't done that. But yeah. So I've written some interfaces to ETS tables, things like this for it. Unfortunately, if you want to make this compatible, you can't keep your tables in ETS tables because there are some table operations that need to be done from the Prologue side that I can't map into ETS. So I can add things to the end of, if I have a sequence here, like parents, I could add a parent. I could add, let's see if this works. I can do assert, see if I can remember this. It's assert Z. It was a while since I was playing with this parent, and we can make another parent, another mother here. Do we have a female? We'll make Liz, and we can make Bob like that, right? Let's see if this works. Yes, and now let's see if I can do my mother again here. We do Pam and Bob, we do Pat and Jim, and we do Liz and Bob. So I've added an extra parent in there, which I can do, right? There are no more, right? That's great. But what I can also do is I can add something to the front of the list, right, to the table. So I can say assert A here, and we want another woman here. We'll say Anne. We haven't had an Anne before. No, we'll do Anne. And we'll say Anne is a parent of Tom. We're doing assert A, so this is putting this at the front of the parent structure here. And now if everything works, we now do mother and we see Anne and Tom because we're seeing Anne and Tom first. And we're stepping down the other ones we got as well. That I cannot do with an ETS table. Put something so it ends up being first. There's just no way of doing that. Put so it ends up things being last but not being first. Which means I can't use an ETS table to keep these structures in. They're just kept internally in a dictionary actually, or a map. So there's just some implementation problems doing this. If I'd accepted not being able to assert A, then I could have done it, but I didn't. Yeah. So the luerl code, I just want to show one thing with luerl code and we're done. And if we just let this run while we're working here. So we'll leave that for the time being. We'll go here, we'll go here. We'll start up another shell as well too. Oh, yeah, we'll get rid of this one. And we will just get rid of those. So what I've done here, these are my spaceships, okay? So if we go to ship demo here, what I can do is I can start up, I've made a little shell that does this. Run ship. This starts up an Erlang, but has loaded in the put a link into the luerl system, and also it starts it up in distributed mode. And why I'm doing that, we'll see in 1 second. Okay, so now I can open up the universe, By the way, for those who don't know, there is a way of defining your own shell commands in the Erlang shell, which I've done here. So we're going to start up 500 chips. Let's see if I get everything right. Our space is going to be 500 by 500 big, and I'm going to start up 2,000 spaceships. So what we see here is the space, here is the universe. Okay, this is the size of the universe. There are 2,000 ships here, but we don't see them yet. What is that thing doing there? Yes, okay. So, right. So what we do now is we're going to start the run. What I'm seeing here is information that the graphics is getting from me moving the mouse across it, which is very irritating. That's what's happening there. So now we start a run, and now I'm going to put a clock tick in here. So we're going to ping every spaceship every 75 milliseconds. And now we start seeing them. Now they're all moving here. Okay. So these are the spaceships moving around here. Now, all these ships are written in Lua. So if we do p luerl/ship demo, we go here and we go Emacs, for example, and we look at our default ship. This is the Lua code that controls the default ships we're seeing here. So it has a number of predefined interface functions for it. We can start the ship. It defines a local table. Every ship's defined a table and has these imports to it. And we can move the ship around here. And these ships are very simple. What happens is they just move in a straight line until they hit the edge of the universe and they bounce off it. That's what's going on here. Okay. That's great. We're running ships. So what I'll make another one, make another browser here. So what I want to do now is just show a little bit about it, a little bit more with Observer. So if we do -sname, we start this off, we'll call this obs, and we'll set the cookie to ship demo. So now we're starting up another Erlang here. And what we can do now is, if we want to, we can start Observer here. So we're going to run Observer distributed over the system, running Observer on one node, inspecting another node. So now we run up Observer, and down here we're getting up Observer. So here we have Observer. And that's where we're going to put this. We're running out of space, but never mind. So now we're running Observer. And now I can see here, if we go up to the Observer, I say which nodes, I want to look at Sim. So now I'm looking at the simulator node. And we can see how many processes we're running. Error occurred on the local node. What happens? No down, sim, absolute. What happened there? See if it works now. Well, it's connected to it anyway, because it's running 2,000 processes, which we see here. So we'll try and look at the load charts, for example. So now I can see the load here, and we can see each one of these is running 12 schedulers, and we see the load here on the schedulers. Okay, they're keeping a pretty well load balanced for as well. And we can see the memory usage, and we can see other things. We can see the memory allocators, which I cannot explain to you because I don't know. We can see it. We can look at processes if we want to. And we're seeing we're looking at processes on the other node. So I'm running Observer on one node, monitoring another node and getting information from it in the load charts. Here we see it decided to dip. So let's have a bit of fun, right? So what we can also do here is I can load in new Lua code to handle the ships. So we'll make a run ship. That, and we'll set the first, say, 1 to 700, make them run ships, right? And now we're going to see that we actually loaded in new. That's the spike was we were recompiling and loading this code, and we see the run ships have gone green and they have different semantics. So when a run ship gets near the edge of the universe, it actually starts following the edge of the universe and goes around about this. And now we're running these, right? We're just doing this. Okay. So now we're running these, and the run ship, the code for the run ship is different. So here is the run ship. The Lua code for the run ship is different. It's got the same interface functions, but it's different. And by the way, this is how we define the shell commands. A module called user default. If you've got that, the exported function there can be run as shell commands. That's why I'm doing the start and the start runs, and I was doing the set ships as well. Okay. So now I just want to do one final thing, and we're done here. Again, if you have questions, please write me here. I keep my user default. Well, I keep it in the source directory where I've kept other Erlang files for this. So let's see, where are we? Wait, we're up here. Sorry, I'm in the wrong place. That's why.
Then you kind of get a system shell that evolves over time.
Sorry. Yeah, I don't.
If you keep on with the source code, then you evolve like a system shell that everyone uses.
Yeah. So here I've got a shell as well too. So here we can start doing some fun things. This is what I'm saying. This is great. So I can do erlang : system flag or system info. We'll start off with system info, and I can see schedulers online. If I can spell it correctly. This is saying how many schedulers I'm using. If everything's correct, that should return 12. Now I can change the number of schedulers I'm using here. So I can do system flag, and I can do schedulers online, and we'll say, what do I press now? And I'm going to kill this one because then we stop everything. So I pressed the wrong button there. We'll do system flag. So I can change the number of schedulers I want to use explicitly. So I'll say I'll just use 10 of them. And I'll do 10. And if we look in the load chart here, we see 2 schedulers was shut down and the load in the other one's increased. The process has moved across for it. I'm just doing this in runtime while everything was running here. Okay. So I wasn't doing anything. The system wasn't being stopped. I could probably even pop it down to 9. We can probably pop it down to 8. Then we're pushing it, but yes. So I'm running 8 schedulers, and we see the load went up. Another 2 shut down. And if we want to, we can go back to 12. I can't do more than 12 because that's the limit set there. If I do that, we see that they've been restarted again. The loads dropped down again. So I can play around with these things while it's running. I just want to show one more thing, and then we're done. So I can also set, this is a game, right? And one thing we can do in games is we can kill things. Attack ship. Like that, we'll set 100 attack ships. So we will set 800 to 900. To 900, yeah. And they'll go orangey. And they kill things. So when a ship gets very close in front of them, they zap it and kill it. And here we see the ship's dying, and we've got sound going boom. I don't have a sound generator for it, and we're shipping here. And if we look here, we see that the load is dropping because the ships are dying. The memory usage is going down because the processes are being reclaimed and everything like this. We're still keeping pretty well load balanced here. And this is what I meant before. I'm not very much into graphics. So these little lighter yellowy things popping up, they're explosions, okay? We're dropping down. And here we see it's starting to think about shutting down schedulers on its own because the load is going down. It didn't change its mind, but it's doing that. And if we just kept this going, it will do that. So these are some of the fantastic things going on in the Beam and the doing the observer. And I just want to point out that everything observer does, you can do yourself if you want to. It's not doing anything weird or strange like this if it doesn't. Yeah, I want to show one case here. Let's see if I get this one correct. I just want to do one more thing. We'll stop this one now. We'll stop this one and just kill it. And I will start it again. Let's see if I get the right thing now. We'll start this again. We'll do start. And we'll just do 400 by 400, so it's easier to see around it. We'll start up 1500 chips. 4, and this pops this one up. It's a bit smaller now, so it's more space. And then we do start run. And then we do 75 again. I can change the ping time, but this is about. So for example, if I set it to 50, everything will start moving much faster. Okay, and now we can observe this one. So we can observe the simulator, and I'll probably have to go look for a connect node, and we connect. Oh, I've stopped this. Never mind. Have to be slightly careful, so I don't start killing things. Yeah. Just to observe the call and start again. I want to show you something fun here. Yeah, this one. Now we're up and running here, and now we look on the sim, and we see what's going on here. We see all these things are going. The load's quite high now because I've got I lowered the ping time for it, so we're running quite a lot here. But what I want to do now is I want to show one thing why you should be very careful using synchronous communication in distributed systems or in concurrent systems. So what we're going to do now is we're going to set chips, and we're going to set all of them. We're going to set them to, if we get the right one now, follow ship. If I got this correct now, what follow ship does is that it, if it sees a ship close to it, in front of it, it tries to follow it. Okay, let's see if I got the right one. I've got two, so I think this is the one that does it. Oops, no. Ah, I'm in the wrong place. That's why. I should be here, of course. 1 to 1500. Yeah. Now they've all become follow ships, and what they have a slight bug in the code. So they go synchronously ask a ship, if the ship is close, what is your speed and your location? And then they'll sit and wait for the reply. And they won't do anything until they get a reply. They can't be pinged to set the time up until they get a reply. So all the yellow ships here, they're following other things. And you see they're all hanging up because they're all doing synchronous stuff. And if we go down here, and we see if I can see it here. We're doing a move here. If here we're actually trying to ping the other ship and get it back again, right? Yeah, this is the moving bit, but up here we're trying to read the other ship and get it. And this is the problem you see here. They're blocking each other. Sometimes they get away, but then they'll get caught and blocked up, and they'll end up stopping. So this is a very, very good example of why you should be very careful using synchronous communication in concurrent systems. Right? That's because they're asking for. They're calling the ship the get pos. So that is a synchronous call to get the other ship's position. It just sits and waits there. And sometimes it works, but we see the things are stopping as well too. I had one called flock ship, which was better, but that didn't do the same job. Yeah. Okay. That's about it. Questions, please. If you have comments, if you'd like to show me, try to see if I can show something else. If you have questions for us, well.
Yeah, it looks like we have just a couple minutes left. Does anyone have any questions though? I'd like to take the mic and ask Robert. A lot of thanks. Robert, we love having you here. Thank you so much for being a part of this.
Okay, that was great fun.
Thank you.
We'll have this up on the recording up online, and thank you. It's,
okay.
It's awesome.
Okay.
Thanks everyone for joining us. And I guess
Hold on, do we have hype for next month?
Yeah,
Kevin.
Well, we have Chris Keithley, I believe, planned next month, and then following that, Bruce Tate.
That's the hype.
Yeah, flock ships were the ones that work. Follow ships are the ones that hung. Yeah. And we saw the load increase here when I made some work. But yeah, this is just an example of why you should avoid synchronous communication in concurrent systems. So be very careful using it, right? Because this code here is get the ship's position of the leader. If there's a leader, it asks, where are you? and also, and then finds out where it is in relation to you and works out, try to speed to do that. And that just hangs the system because we're doing synchronous communication. But yeah, that's just the way it works. This was added to show this, by the way.
I have a use case for luerl, so I'm excited. I hope I get to do it.
Sorry?
I have a use case for luerl. I have like an ERP system I want to add some amount of scriptability to.
It's actually luerl's being used in real life, in real products. One is there's a bank in Hungary called OTP Bank. It's its real name, the OTP. I don't know what it stands for in Hungarian, but it's a real bank. It's quite funny walking around in Budapest and seeing, especially in the evening, seeing OTP Bank in lights there, seeing for it. What they have done is they've rewritten part of their backend in Erlang, and they wanted to be able to add scripts, dynamically add scripts without having to recompile the Erlang code and make new releases. And they thought, okay, they could do that in Lua, and they use luerl to implement the Lua scripts. Do that. So that's running in the real world. Another one is a gaming company called Creative Assembly. What's their game? One of the war games. I can't remember which one it is now. It's a very big one. We will find it. Yeah, they do the games. That's the whole. It's the Total War series. They're the ones doing Total War series. They're not, as far as I know, they're not using luerl in the game itself, but in the interface to the users, they want to be able to write that in Lua, and they're using luerl to do that as well too.
It makes sense because you want that to be dynamic.
Yeah, that's why. So they can go in and change things as well too. It's being used in other game places as well. I cannot remember, but yeah. So it is actually in use. And I know, I don't know of any explicit use of erlog. If anyone here's a one, please tell me. LFE is also being used. If you go back and look at the Code Beam v America presentations when they're released, look by one by Duncan McGregor. He's been using it to program music, which is also quite fun. He's also one of the people who's been working on it as well too. So if you go into the lfe.io site, he's done most of the graphics and the documentation there. So yeah, and now we see our spaceships are almost all hung now, but they're getting there. Yeah. Okay, so the things are being in use. It's slightly scary, but yes. Well, it is. I mean, the banking world is not for fun. And yeah,
surely, yeah. So anybody doing that ought to have robust enough testing procedures that something like that couldn't catch them off guard, or else they already were negligent.
Yeah, and of course, seeing. I mean, I didn't mention this, but each spaceship here is its own Erlang process. So each spaceship is its own Erlang processes. Here I'm running 1,500 Erlang processes, each one running its own little Lua code for its own little Lua system. One of the things I reckon which made it safe for the bank was that, okay, if one of these processes crashes running a script, it's not going to crash the rest of the Erlang system. This is just going to crash an Erlang process. So in that sense, it's quite safe. And I think also the fact that they can have separate script environments. They can pop up a new environment to run a few scripts and then pop up another one and things like this, which means they don't interact. And so they don't have to worry about sharing environments. And if they're running on one Lua system, to share environments to make sure each invocation has its own separate environment, things like this for it, which Lua is not designed to do. Because they get this by default. They just start up a new process running luerl, and that process has it's completely its own environment. And it's sandboxable. Basically, for normal Erlang Elixir is not sandboxable. You cannot sandbox it. If someone gets in on your code, gets code in your machine, they can do whatever they want if they know what they're doing. I mean, simple. I running code, I do processes and get a list of all the process PIDs running on my node, and I kill every 10th one. There's nothing stopping me doing that. If I can get code in, I can do that. What you can do in the luerl system is that it's seeing it's running in its own environment, its own memory and everything like this. It's relatively easy to sandbox. You just turn off all the things that interact with the outside world, outside the sandbox, and then it can't interact with them. It can load new Lua code, but that Lua code can't get out because it can't get out of the things for it. If you want to write Lua code that talks to the outside world, then you have to implement that in Erlang, and that you cannot load from Lua. You can load it in from the outside, but you can't load it from Lua. So it's sandboxable, which is also a big benefit for doing things. And it's just one of the things you get for free when you're doing it. So yeah, and it's fun doing it, and the work's progressing in all of them actually. So yes, hopefully they should all come with a new major release soon. But yeah.
Awesome.
Well, I think
I have one question actually.
yeah, go ahead. Jeff.
I don't know anything about flavors, but I saw that Lfe you were working on flavors, and so I was curious what it's like objects, right? It's one of the early objects.
It's an older version. It came from the Lisp machines before the common Lisp, the close and things like that for it. It's not you're not implementing classes and class hierarchies as such. You're implementing flavors in the sense like cooking, right? When I cook something, I can chuck in lots of flavors I want to it and mix them all together and get them. I can do it I've got much more choice of how I want to mix things with flavors than if I'm doing.
That's right. It was one of the first or the first mixins implementation, wasn't it?
Yeah.
Yeah.
So I can make a class system with a class hierarchy on top of flavors if I want to. That's perfectly okay, but I don't have to do that. So I can just chuck things in. For example, if I want to make a car flavor, I can say, okay, I want this body, I want these type of tires or flavors for those, I want this type of engine flavor for that one, and put all these things together.
How big of a lift do you think it is to take flavors and Lfe and get something akin to a Smalltalk system running on it that's easily editable?
I don't know. The problem is that when you're running Lfe and with flavors, you have the Erlang. You can't get around the fact you have the Erlang module function handling system, right? That there's just no way around that. The code handling is the same. But you can combine them and you can work with them. Flavors by default uses processes for instances. So you're doing process communication, which makes them heavier than say what you would have inside of Smalltalk, where flavors are much more baked. Well, sorry, where the instances are much more baked into the system. Right? There's no real way of doing that efficiently in Erlang. It's just not designed to do that.
Sure.
That's a problem with it. That's why if you look in Erlang, in the Erlang world, there've come a number of attempts to add object orientation, but none of them have really survived. Not doing classical object orientation.
I don't really want classical object orientation. I want processes that I can do stuff in a sort of environment, like in an image style.
Well, you can define flavors to that. I mean, you can define a flavor. It will have a set of methods. It will have instance variables and things like this for it that you can combine them, put them together with other flavors and make a more complex flavor and stuff like this. Yes, you can do that. It's sort of like structs on steroids. I can put these things together, and there are ways of defining them so they work together. And when I make one, I can say, when I make this thing, I want to put these together. And when I make it, it will compile code that does this for you and things like this for as well too. So it does quite a lot of that. It was a bit of an experiment to do that. And I just thought the old Lisp machines were a lot of fun. But, that's why.
Yeah, Feynman's son worked at one of the Lisp machine companies.
Sorry?
Symbolics, maybe. I think Richard Feynman's son, I think, worked at Symbolics or somewhere, one of the Lisp
Okay.
machine companies.
Okay.
Or not Symbolics, it was definitely another one.
Hmm.
Anyway,
Well, there were two
all right,
main
cool.
ones, Symbolic and LMI. This Machine Incorporated. These are the ones that came out of MIT. And which company was it? Had the other one? Had one as well too. The other company. But yeah, there were a few that did Lisp machines. Or yeah. Let's see if I can find out the name of the last one, I think.
The Connection Machine. Thinking Machines Corporation, TMC.
Okay, yeah. And Symbolics, yes, and we had one from Texas Lisp machines. But
Yeah,
Texas
I had it
company
wrong. The Lisp machine was the front end, essentially, for their supercomputer. All right.
Yeah. No, I think Lisp machines they're a lot of fun. I know you can run simulators for them now, but I keep losing them. But yeah, that's where I got the influence for the flavors from the documentation. So I thought that would be fun to try and implement it. As I said, there've been a number of attempts to put object orientation on top of Erlang system, but it just hasn't really worked. Unless, of course, you ask Joe. Joe said Erlang is the most object-oriented language in the world because it's the way.
Well, Alan Kay recommended the same, and I think he carries some weight in that definition.
Yeah.
Space.
Well, from Alan Kay's point of view, that's where Joe got his from. Alan Kay's point of view, the most important things object orientation are the object isolation and message passing. That was, in his point of view, the most important things in object orientation. And what do we do in Erlang, in Lxd and Lfe for that matter? Well, we have object isolation and we do message passing. Okay, that's not what 95% of the object-oriented community assume is base of object orientation, but that's why.
This is also why I want to figure out how to do something like a Smalltalk, but on top of Erlang. It just seems like that's the obvious place that ought to go.
Yeah, you could do a lot with that. I think the problem is that it makes objects heavier. The communication between them becomes much heavier than you expect a normal object, say a normal Smalltalk. That's the downside of it. That's the downside of using flavors as well too. If you compare to using flavors, say, in a Lisp machine, where they do have a concurrency, but not the level we're talking about. And their flavor instances are more just things, right? The big whopping data structure, rather than we're doing as a process. Again, that's just a choice how you want to implement it as well too, what properties you want. But yeah. There's a question about the newer languages. They're coming, a bunch of them. There have been experiments doing statically typed functional languages on top of the Erlang system. As I said, I mentioned two of them. There are more come as well too. Gleam, I think, yes, there's another one too. They haven't really hit off yet. Hit off in the sense that people are using them seriously in products. I think that's the problem.
Yeah, I forget the name of it, but there's one for essentially compiling Elm down to what amounts to a gen server, and that seems like a nice spot because you get a lot of compiler guarantees about the types, but obviously that gets thrown away once it's in the system. Yeah.
And as I said, the WhatsApp group were looking at that for a while. We're doing one because that's what I mean. They're very much into still using Erlang, but they were thinking of maybe having, if you have a statically typed Erlang, it would be a better system for building better language and underlying system for building large products in. But well, unfortunately, they put that on the shelf for the time being anyway. Anton Lavrik, their leader, he gave a few talks about that last year. What they were doing. So it's definitely interesting. And as I said, I like Lisp. I like the Lisp language, the syntax itself. It's very nice. I think it's easy.
All right. Well, thanks again for coming and talking to us. Probably
Yeah.
good.
By the way, if you look at the spaceships, they've almost all stopped now. There are a couple down the bottom right-hand side which are moving, but everyone else is locked. So yeah. Sorry, that's just yes.
No, it's good.
I don't think if I've got the there. It's still doing some load. Well, you see, it's shut. It's only actually running 2 schedules now at the moment. So those processes just been moved across to 2 of them. So it does work all this stuff. And eventually they will stop all of them. They'll go down even more. Okay, yeah. So you have to stop me, otherwise I'll just keep going. But, yes. Any final questions? No. It was great, by the way, you could do this during the day in your time.
It was a fun experiment for us. We had a ton of people show up, so it seems successful.
Okay, oh, that's nice. Yeah. Yeah, otherwise it gets a bit late.
All right. Well, thanks for coming, everybody. I'll see you all next time.
Thanks, Robert. Thanks, everyone.
Okay, goodbye. Thank you very much.